Hello everyone. Today the topic we will be talking about is Introduction to Dynamic Programming. Hopefully we already know the previously discussed algorithm design technique, divide and conquer. In the divide and conquer algorithm design technique, what we do, we first divide the problem into subproblems, solve those subproblems, and then combine the solution of the subproblems to get the solution of the actual problems. One of the example of using divide and conquer algorithm design technique was merge sort. Another example is quicksort. We will be talking about two new important algorithm design techniques. One, dynamic programming, and second, greedy algorithm. These are very useful algorithm design technique to solve different kinds of problems in practice. Today's topic is dynamic programming. Historically, the word programming in dynamic programming and computer programming has no relationship. The programming in dynamic programming has been used long before the computer programming was introduced. Dynamic programming is a very powerful and general tool for solving certain optimization problems. So, what is an optimization problem? Optimization problem is a problem where you try to find the best solution from all the feasible solutions. One of the examples can be, let's say you are in city A. You want to visit city B. There can be a lot of ways you can visit city B from city A. One of the examples of an optimization problem finding the path from city A to city B can be you try to find the shortest path from city A to city B. The dynamic programming is kind of easy when you understand the concept. And at the beginning, it may look like magic, but when you see enough examples, it will be very easy for you to apply the technique to solve different algorithmic problems very efficiently. Let's see an example. So we all are familiar with Fibonacci numbers. Fibonacci number start from 0 and goes to 1, 1, 2, 3, 5, so on. There is a recursive definition for the Fibonacci number. We can tell this is a Fibonacci sequence. So Fibonacci sequence have a recursive definition. It has two base cases. These first two numbers are predefined. 0th Fibonacci number is 0. First Fibonacci number is 1. These are called the base case. Other than the 0th and 1st Fibonacci number, if you try to find any other Fibonacci number, you use the recursive definition. So what you do, when you try to find the nth Fibonacci number, you calculate the n minus 1th Fibonacci number and n minus 2nd Fibonacci number. Then add them together to get the nth Fibonacci number. This is kind of called the recursive case. So how can we compute nth Fibonacci number or f of n? We can write a simple computer program to calculate the nth Fibonacci number f of n. If you write the computer program to calculate the f of n, it will look like something like this. We can use the recurrence or recursive definition of the Fibonacci sequence to write down the recursive algorithm. So we name the Fibonacci function fib and it takes one argument n. At the beginning, what we do, we check whether the n is 0 or 1. If n is 0 or 1, we return n as a result. That means 0th Fibonacci number is 0, first Fibonacci number is 1. If n is not 0 or 1, then we use the same function to calculate n minus 1th Fibonacci number. Calculate n minus 2nd Fibonacci number, and when we get the result from those two function call, we add them together to get the nth Fibonacci number. This is how we can write a recursive algorithm to find out the nth Fibonacci number. So now the question is, what's the time complexity of this algorithm? One way to find the time complexity of this algorithm, we can use the recursion tree method. And find out how much work this function is doing. So if you think about what are the work this function is doing, this function is doing some constant time work to check whether n is equals to 0 or n is equals to 1. Then it is calling the same function recursively 2 times. But for the first function, the input or the argument of the function is n minus 1. For the second recursive function, the argument is n minus 2. So if we try to write down the runtime recurrence for n, what we can write is Tn minus 1 plus Tn minus 2 and some constant work. Let's take a look at the recursive tree or recursion tree for this recursive Fibonacci algorithm. If we try to find out what is the ninth Fibonacci number, what we should calculate? We should calculate what is 8th Fibonacci number, and then we should calculate what is 7th Fibonacci number. For 8th Fibonacci number, we have to calculate what is 7th Fibonacci number and what is 6th Fibonacci number. Similarly, to calculate the 7th Fibonacci number, we have to calculate 6th Fibonacci number and 5th Fibonacci number, and so on. The tree will go downwards. So when we will stop? We will stop when we reach at the base case. So first of all, each node in this tree has 2 children, because in our previous recursive algorithm, we have 2 recursive call. Now try to find out how many nodes are there. To find out how many nodes are there in this tree, we have to find out what is the height of the tree. If we take a look at the height of the tree, we can see the height of the tree is not equal on the left side and the right side. Why not equal? Take a look at the pattern here. So on the left side, n starts at 9, then goes to 8, again goes to 7, then goes to 6, and at the end it will go to 1. That means in this side, the height of the tree will be n. If we take a look at the right side, n starts at 9, then goes to 7, then goes to 5, then goes to 3, and so on. So in this side, the height of the tree will be n by 2. So if we try to draw the approximate tree, it will look like kind of this. So now the question is, how many nodes are there in this tree? If the tree height was n by 2, then we will have 2 to the power n by 2 nodes in that tree. Why? Because the tree will be a complete binary tree. If the height of the tree is n, then there will be 2 to the power n nodes in the tree. But our tree is not 2 to the power n by 2, or does not have, it may have 2 to the power n node. So in terms of our tree, the number of node will be between 2 to the power n by 2 and 2 to the power n. In other words, the runtime of our algorithm will be exponential. We can write the runtime of this algorithm is kind of 2 to the power n, as we can ignore some of the lower term power of 2. The exact runtime of this algorithm is O of 1.6 to the power n. Now let's talk about the problem with this recursive algorithm and why the runtime is so bad. We know the exponential runtime is pretty bad. And now we try to find out why the runtime of this algorithm is exponential. In other words, why it is bad. If we take a look at here, let's say we started with 9. We calculated 8, 7. When we calculate 8, we calculate F7, F6. When we calculate F7, we calculate F6 and F5. So these are actually the recursive calls when we started with F9. So all the nodes in this tree are kind of recursive call. In other words, these are the sub-problems or the previous node. So these two are the sub-problem of this. If we take a look at here, we can see say how many times we calculated F6. We calculated F6 here, F6 here, we calculated F6 here. So we calculated the same subproblem 3 times. If we try to find out how many times we calculated F5, we calculated F5 here, we calculated F5 here, we calculated F5 here, we calculated F5 in this, and we will calculate another F5 here. So F5 is actually calculated 5 times. Previously, F6 was calculated 3 times. So as you can see, we solved the same subproblems multiple times. And this is why the runtime of this recursive algorithm is very bad. So how can we avoid that? One of the way to avoid that is we can pre-compute all the subproblems that may be needed. So if you think about it, when you try to find out what is F9, what are the distinct subproblems you have to calculate? From the base case, you have F0 and F1. You have to calculate F2, F3, F4, and so on, F8. So these are the distinct subproblems you have to calculate. If you have the solution of these distinct subproblems, you can calculate F9. So if you think about the relationship between n and the distinct subproblems, then you can see the distinct subproblem is kind of order of n. That means the number of distinct subproblems you may have to solve does not grow exponentially, it grows actually linearly. Another way to address the problem of solving the same subproblem many times, you can compute the subproblem on demand, but you have to memorize the solution to avoid the recomputation. That means, let's say you calculated the subproblem F6 here. Then, when you try to calculate the F6 in this node, you will not call these two, you will not call these two subproblem. You will use the result of this subproblem, which should be stored somewhere in the memory and return from here. So these are the two ways you can avoid the exponential runtime, and you may end up in a very good runtime which is linear. Now let's see how can we convert the exponential runtime algorithm into a linear runtime algorithm using converting the recursive algorithm into a iterative algorithm. The way this algorithm works, it creates another function called fill, which takes an input n or argument n. At the end, it will return what is the nth Fibonacci number. The way this algorithm works, it creates an array with size n plus 1. The size of the array is n plus 1, so the last index is n. First, it uses the base case and populate the first two numbers in the array. First number is 0th number, which should be 0, not 1. And the first number is 1. That means 0 and 1. Next, it has a for loop. For loop goes from 2 to n. From 2 to n, and it calculates For each index, it calculates what is that indexed Fibonacci number. So first it calculates F2 using F1 plus F0. So F1 is 1, F0 is 0, so F2 is 1. Next, it calculates F3 using F2 and F1. F2 is 1, F1 is 1, so F3 is 2. Similarly, F4 would be 3, F5 would be 5, and so on. At the end, it will calculate what is the Fn using this for loop. This for loop should end here. And when the for loop ends, we return here. That means we return the last indexed number, which is n Fibonacci number. Now, if we try to calculate what is the time complexity of this algorithm, we can easily figure out that the time complexity of this algorithm is order of n. Why order of n? Because we have to calculate the n Fibonacci number. We have to calculate these numbers, which are kind of n minus 2. So we can ignore constant, which essentially order of n. There is another thing to consider in this algorithm. In this algorithm, when we try to calculate the nth Fibonacci number, we created an array of size n plus 1. So in this case, we can talk about the space complexity also. For this algorithm, the space complexity is again order of n. So from our discussion, we found out that the time complexity of this algorithm is order of n and space complexity is also order of n. Now there will be a quiz for you. I will upload a link in the Blackboard so that you can submit your answer. The quiz would be you have to write an Fibonacci number algorithm for which the time complexity will be order of n, but space complexity will be order of 1 or constant. So this is your quiz question. We all know that when we have a recursive algorithm, we can convert the recursive algorithm into an iterative algorithm. So now the question is, can we always speed up the recursive algorithm's runtime by converting it into a iterative algorithm? The answer of this question is we cannot always do it. One of the example is merge sort. If we don't see a overlap between the subproblems we are creating, then we will not be able to improve. The reason behind why we improved the runtime of the Fibonacci number algorithm was we had a lot of same subproblems occurred in different times. So what we did, we memorized those recursive subproblems answer so that we don't have to recalculate them again and again. But in case of the merge sort, if this is the bigger array we try to sort, the first we divide it into two halves and we use the recursion to sort these two halves of the arrays. And we don't see any overlap between these two subproblems. That is why we cannot improve the runtime of the merge sort by converting it to a iterative merge sort. So how will we know whether we can improve the runtime using the iterative solution from a recursive solution? In other words, how we can know whether we should go for a dynamic programming or not? There are some characteristics we have to look for. The problem that we can solve using the dynamic programming technique have two properties. One is called the optimal substructure properties. What the optimal substructure property says, optimal solution to the original problem contains the optimal solution to the subproblems. In other words, if we think about our Fibonacci number problem, when we calculate f of n, we use the solution of f of n minus 1 and the solution of n minus 2. So what the optimal substructure is saying, the optimal solution of f of n will contain the optimal solution for f of n minus 1 and f of n minus 2. The second property of the problems that can be solved by the dynamic programming is overlapping subproblems. So what is the overlapping subproblems? We will see the same subproblem that will appear in many solutions. As we have seen in our Fibonacci number algorithm, we have seen F6 occurred 3 times, F5 occurred, I believe, 5 times, and so on. The way the dynamic programming take advantage of these two properties are when you calculate the solution for one subproblem, you memorize the solution of that subproblem and then reuse that solution later on when the same subproblem occurs again. So that is called the memorization and the reuse of the same subproblems. When you see the problem has the two properties that we have discussed, overlapping subproblems and optimal substructure properties, then you can tell that we can solve this problem using dynamic programming. So there are two steps when you solve a problem using dynamic programming technique. One, you have to formulate the solution as a recurrence relation of solution of the subproblems, what we did in our previous example. So f of n was f of n minus 1 and f of n minus 2. We used this recurrence relation to solve a bigger problem. Then you can specify an order to solve those subproblems so you always have what you need. To do that, there are two ways. One is the bottom-up approach. What we have seen in the iterative version of the Fibonacci number is the bottom-up approach, where we tabulate the solution to all subproblems before they are used. Sometimes it will not be possible. So what if you cannot determine the order at the beginning? Or what if you don't need all the subproblems? In that case, what you use is called the top-down approach. In the top-down approach, you calculate the solution for some subproblem when they are needed. And when you calculate the solution for one subproblem, you remember that solution. So let's take an example. In our Fibonacci number problem, let's take an example when we try to find out what is the F4. So you call the fib function. In the fib function, you check whether n is 0 or 1. Here, n is neither 0 nor 1. So you call the F3. When you try to calculate the F3, you call F2. And when you try to calculate the F2, you call F1. At this time, you return 1 from here because you know the answer of F1. So you call the F0 from here and you know the answer of F0, which is 0. When these two function returns, you calculate F2, which is 0 plus 1, 1. So what you have to do, you have to memorize that answer at some table in the memory. Then you go on. You from the F3, you call F1. You know the answer of F1, so you return 1 from here. F2 is also 1. So now you can calculate F3, which is 2. So you return 2 from here. Now you call F2. At this time, usually what you had to do was you had to call F1 and F0. But as you already know the answer of F2, you will not call these two functions. You will return 1 from here. So from these two numbers, you will calculate F4, which is 3. So this is what the top-down approach is. You started from the top and you calculated numbers when they are needed and memorize those answers when you calculated them. So when you try to calculate the same number or same subproblem again in the future, you don't call the recursive function, but you use the answer from the previous calculation. So that's end of the first problem. We will see use the dynamic programming.